All right, so we've really been working a lot with the idea of what makes something a solution and how many solutions there are and how that can look different depending on the type of problem. And so in this video, I'm just going to take you through a few different examples where we find a solution or the solution or all the solutions and seeing how they're similar and how they're different from each of those different situations. So let's look at a problem. Let's say it's a two-step equation, something like 2x, let's go, 2x plus 3 is equal to 9. If I wanted to solve this, I'm trying to figure out what number can go for where x is. What number can replace the letter x to make it true? And if I do some algebra, by canceling the 3 on both sides, canceling the 2 on both sides, I can get x equals 3. And what does it mean if I say x equals 3 is a solution? What it means is that when I go and I say replace x with 3, that I get a number that really equals 9. It works. 2 times 3 is 6, 6 plus 3 is 9. So when I say x equals 3 is a solution to the equation, I'm saying that that is a number that can replace the letter to make it true. Make both sides of the equation the same number. They're both 9 in this example. Okay? Let's look at a slightly different problem, very similar. Let's look at it instead as 2x plus 3 is less than 9. So we just kind of do the same thing. Cancel the 3, cancel the 2, get x is less than 3. The number 3 here, though, is no longer a solution, because we saw that if I replace x with 3, here, I get 9. But the question that I asked you here is an inequality. I don't want the left side to equal 9. I want the left side to be smaller than 9. 3 doesn't count as a solution anymore. A number that's smaller than 3 would count. For example, the number 2 works. If I do 2 times 2 plus 3, I get 7. That's good. 7 smaller than 9. The number 0 works. 2 times 0 plus 3 is 3. That also works because 3 is smaller than 9. I could do negative 100, because that's a negative 200 plus 3, negative 197. That's smaller than 9. Smaller in the sense of being further to the left on the number line. Okay? So how many solutions are there to this situation? Now, there's not one solution. In fact, the old solution of x equals 3 is not a solution to x is less than 3. It's not a solution. 3 is not smaller than 3. But there are an unlimited number of other solutions. There's 2, 0, negative 100. There's other ones like 1.5, 2/3, negative pi. So there's an infinite number of solutions to the inequality. Okay? Now watch what happens when I try to ask the computer to type these solutions. If I tell the computer 2x plus 3 equals 9, notice that we've got a dot where x is equal to 3. If you go up and down this line, the x value is only 3. The x value is always 3, because x equals 3 is the only number that solves the equation. Watch what happens when I change it to 2x plus 3 is less than 9. Now I have a shaded zone. Is the x value always 3 in that shaded zone? No. The x value can be 2. The x value can be 0. If I scroll super far to the left, the x value could be negative 100 and it would be shaded in. All of those decimal points would also count as solutions. So you can see that what the computer is doing, it's the same as what I was doing with my algebra. It was just coloring in, for the equation, coloring in all the dots where x is exactly equal to 3. And for the inequality, coloring in all the dots where x was less than 3. Let's look at a third example. Slightly different situation. We've seen a lot of problems like this. 2x plus 3 is equal to y. I can't even do the same thing here because if I subtract 3 from both sides, I don't know what y minus 3 is. If I divide by 2, I don't know what y divided by 2 is. So I can't get a single answer here. And this is where it gets a little confusing because it seems like the number that we need to know is the y number. We kind of need to know what we're shooting for. What it turns out is that there is an x solution for every y target number, and vice versa. For every y solution, there's an x target number. They come in pairs. They come in x, comma, y pairs. We already know from our first example here that if x equals 3, then we know that y has to equal 9. What if x was a different number? What if we made x equal 2? Then we know from here that if we made x equal 2, it would spit out the number 7. If x is 2, we do 2 times x, 2 times 2 is 4, plus 3 more is 7. So if x is 2, y is equal to 7. We know that if x is 0, y is equal to 3. Those are all 3 points on the graph. And I'll show you what those 3 points look like. X is 3, comma, y is 9. X is 2, comma, y is 7. X is 0, comma, y is 3. Looks like I need to zoom out a tiny bit. But you can see those 3 points are solutions to our 2-variable equation. I can actually connect all of those points by typing in y equals, I can typing in 2x plus 3 equals y, which is the same as y equals 2x plus 3. I just wrote it in this order to match the earlier problems. You might notice, and I hope you do notice, that it has a y-intercept of 3. You might notice that it has an m of 2, because it's going up 2 over 1. The m is 2. But what I really hope you notice is that all of the solutions that we talked about are points on the line. When we did the inequality, all the solutions were x values in the shaded area. And when we did the first equation, which somehow got shifted down, the x value of 3 was the only number that worked. Okay? Now the last thing that I want to do is look at an inequality. 2x plus 3 is less than y. Now here's the thing. We know that if x is equal to 3, that we know that y can't equal 9 anymore because 2 times x plus 3 is exactly 9. So y needs to be bigger than 9. If x is equal to 2, 2x plus 3 equals 7. So now we know that y needs to be bigger than 7. And similarly, if x equals 0, then we know that y needs to be bigger than 3. Let's see if the computer agrees. We can say 2x plus 3 less than y. And I want you to notice what we're seeing here. If x is equal to 3, the shaded in area are the y values that are bigger than 9. All the y values that are shaded in go straight up from the boundary point of 3, 9. all the y values that are shaded in go straight up from the boundary point 2, 7. They go up from the boundary point 0, 3. All of the points on the line are the boundaries to the inequality. Just like when we did the 2, 1 variable examples. The x equals 3 was the boundary, and everything left of it was shaded for x is less than 3. So this was an example of the 4 sort of types of situations we've been solving and the 4 different types of solutions. We've had 1 variable equations, 1 variable inequalities, 2 variable equations, and 2 variable inequalities. And then the only other fun thing is when we start doing more than one at the same time. Like, for example, 2x plus 3y is less than 12, and looking for where things are shaded by both inequalities, or where both boundary lines cross over each other. Okay? Please let me know if you have any questions. Happy to help.